There's a place on this Earth where the temperature drops to -8 to 9 degrees Celsius, where the wind blows at 300 kilometers per hour and the darkness lasts for 6 months without a single sunrise, where the ice is nearly 5 kilometers thick in places and contains 90% of all the fresh water on the planet, where the ground beneath the ice has not been touched by sunlight in 34 million years, and where, underneath all that ice, in absolute darkness at crushing pressure, there are lakes, liquid lakes, and in those lakes, there may be life. Tonight, we are going there. Hello there, and welcome to the Sleepy Science Facts channel. Tonight, we will be drifting into the world of Antarctica. Not simply the frozen continent at the bottom of the globe, and not just the penguins in the ice and the dramatic images of explorers hauling sledges across white emptiness. We are going into all of it. The full, ancient, and deeply extraordinary science of the most remote, most extreme, most misunderstood, and in many ways most important landmass on Earth. Antarctica is larger than Europe. It is larger than the United States and Mexico combined. It holds so much ice that if it all melted, global sea levels would rise by approximately 60 meters, drowning every coastal city in the world underwater. It is the coldest, driest, windiest, and highest continent on Earth, a place where the average elevation exceeds 2,300 meters not because the land is high but because the ice sitting on top of it is so thick. It has no permanent human population, no indigenous people, no trees, no rivers running to the sea. Yet it has been shaping the climate and the oceans of the entire planet for 34 million years, and the changes happening to it right now are among the most consequential events occurring anywhere on Earth. From the ancient lake sealed beneath kilometers of ice to the extraordinary biology of organisms that have evolved to survive conditions that would kill almost anything else, from the history of the continent's discovery and the heroic and terrible expeditions that explored it to the deep geological secrets locked in rocks that have been covered in ice since before our species existed, Antarctica rewards curiosity with something genuinely astonishing at every depth. If you enjoy these gentle journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. But for now, all you need to do is relax. Let your body soften and allow your breathing to slow and allow the day to gently fade away as we explore the mysteries of Antarctica together. Let's begin. Antarctica has not always been a continent of ice. 34 million years ago, it was a warm, forested landmass connected to the other southern continents, home to diverse plant and animal life in a climate not unlike that of present-day Patagonia. The transformation from a green continent to the frozen world it is today was triggered by tectonic plate movement, specifically by the opening of the Drake Passage, the ocean channel between the southern tip of South America and the Antarctic Peninsula. When South America and Antarctica separated and the Drake Passage opened wide enough for ocean circulation to flow through it, the Antarctic Circumpolar Current was established, a powerful flow of cold water that encircles Antarctica and effectively isolates it from the warm water of the lower latitudes. Before this isolation, ocean currents could carry warm tropical water to Antarctic shores, moderating the climate. Once the circumpolar current was established, Antarctica was cut off from this warming influence, and the continent began to cool. Glacier expanded, reflecting more sunlight back into space and cooling the continent further in a positive feedback that drove temperatures lower and lower until the continental ice sheet we know today had formed. The coal deposits found in Antarctica, mined by geologists from exposed rock faces at the edges of the continent, contain the compressed remains of forests that grew in a warm, wet Antarctica hundreds of millions of years ago, when the continent was part of the ancient supercontinent Gondwana and sat in much lower latitudes. The frozen continent is not inherently frozen. It is a warm place that geography and oceanography have kept cold for 34 million years, and the same forces that made it cold could, under different tectonic configurations, allow it to warm again. The ice sheet that covers Antarctica is not a simple, uniform block of frozen water. It is a dynamic system of extraordinary complexity, flowing slowly outward from the high interior plateau toward the coast in vast glacier and ice streams that move at speeds ranging from centimeters per year in the interior to kilometers per year at the coastal margins. The interior of the East Antarctic ice sheet, the larger and more stable of the two major ice sheets that cover the continent, is among the most geologically stable environments on Earth, with ice at its base estimated to have been frozen for over a million years. The West Antarctic ice sheet, smaller and sitting on bedrock that lies below sea level, is considered far less stable and is currently losing mass at an accelerating rate. The ice sheet is not simply sitting on Antarctica. It is pressing down on it, and the weight of approximately 26 million cubic kilometers of ice has depressed the bedrock beneath it by up to 1,000 meters below where it would sit without the ice. If the ice were removed, Antarctica would slowly rebound upward in a process called isostatic rebound, taking tens of thousands of years to reach its new equilibrium position. Much of West Antarctica would still be below sea level even after this rebound, because the bedrock lies so deep that even the removal of the ice would leave it in a bowl-shaped basin open to the ocean. This geometry, in which the ocean can potentially access the bedrock beneath the ice sheet, is what makes the West Antarctic ice sheet potentially unstable in ways that the East Antarctic ice sheet, resting on high ground, is not. Let your breathing settle into its own quiet rhythm. There is nothing to hold on to tonight except the darkness and the cold of a continent that has been keeping its secrets for 34 million years. We are only just beginning to learn them. The lakes beneath Antarctica are one of the most extraordinary discoveries in the history of Earth science. The existence of liquid water beneath kilometers of ice was first proposed in the 1960s and confirmed by radar measurements in the 1970s, when scientists mapping the bedrock topography of Antarctica using ice-penetrating radar found bright reflections at the base of the ice sheet consistent with liquid water rather than ice. Lake Vostok, the largest subglacial lake in Antarctica, was identified beneath the Russian Vostok research station at a depth of approximately 3.7 kilometers of ice. It is approximately 250 kilometers long, 50 kilometers wide, and up to 900 meters deep, making it roughly the size of Lake Ontario and one of the largest lakes in the world by volume. The water in Lake Vostok has been isolated from the atmosphere and from the surface world for an estimated 15 to 25 million years. The lake remains liquid despite the temperature of the ice above it being around minus 55 degrees Celsius because of two factors. First, the pressure of the overlying ice lowers the melting point of ice, meaning that the ice at the base of the sheet can be melted by relatively modest amounts of geothermal heat from the bedrock. Second, geothermal heat from the Earth's interior, the same heat that drives volcanism and plate tectonics, flows upward through the bedrock and into the base of the ice, melting it and maintaining the lake. Lake Vostok is not alone. Over 400 subglacial lakes have now been identified beneath the Antarctic ice sheet, ranging from tiny ponds to enormous bodies of water. Some of these lakes are connected by subglacial rivers that flow beneath the ice in channels carved by the pressure of the water, carrying water from one lake to another in a drainage system that operates entirely in darkness, under kilometers of ice cut off from the surface world above it for millions of years. Whether there is life in Lake Vostok is a question that has occupied scientists since its discovery, and the answer, still emerging from analyses of water and ice samples from the lake, is one of the most significant in astrobiology. The conditions in Lake Vostok are extreme by any measure. The water is cold, at approximately minus 3 degrees Celsius, kept liquid by pressure rather than warmth. It contains very little organic matter compared to surface lakes. The pressure is enormous, approximately 350 times atmospheric pressure at the surface, and it has been isolated from the light, the atmosphere, and the nutrient inputs that sustain most life on Earth for millions of years. Yet preliminary analyses of ice cores drilled into the accretion ice that forms at the lake's surface where the overlying ice sheet melts into it have found bacterial DNA, suggesting that microbial life may persist in the lake in forms that have adapted to these extraordinary conditions. The organisms, if confirmed, will be among the most isolated and most extreme on Earth, living in conditions analogous to those proposed for the subsurface oceans of Jupiter's moon Europa and Saturn's moon Enceladus, both of which are thought to have liquid water beneath their icy surfaces. The discovery of microbial life in Lake Vostok would not confirm that life exists on Europa or Enceladus, but it would demonstrate that life can persist in liquid water isolated from sunlight and conventional energy sources for geological timescales, making the possibility of life in similar environments elsewhere in the solar system significantly more plausible. The lake beneath the ice at the bottom of the world has become one of the most important windows in the search for life beyond Earth. Antarctica is the driest continent on Earth, despite being covered in 90% of the planet's fresh water. The paradox resolves when you understand that Antarctica is technically a desert. A desert is defined not by heat but by aridity, specifically by annual precipitation that falls below 250 millimeters, and Antarctica receives so little precipitation that most of its interior qualifies as desert by this definition. The precipitation it does receive falls almost entirely as snow, and in the dry valleys of Antarctica, the most arid regions of the continent where the mountains block the ice sheet and katabatic winds evaporate or blow away any snow that falls, the ground has been snow-free and dry for thousands of years. The McMurdo Dry Valleys are the largest ice-free region in Antarctica, covering approximately 4,700 square kilometers, and they are so dry and so cold that they have sometimes been described as the closest environment on Earth to the surface of Mars. The soils of the dry valleys are among the oldest, most stable soils on the planet, undisturbed by glaciation, by rain, by the burrowing of animals, or by the roots of plants. Some soil surfaces in the dry valleys have not been disturbed in more than 10,000 years. Yet they are not lifeless. Microbial communities live within the rocks themselves, in tiny air spaces between mineral grains just below the surface where they can access the faint sunlight that penetrates the translucent rock, and a small amount of liquid water produced when the rock absorbs solar radiation and warms enough to briefly melt the tiny amounts of ice present in the rock pores. These endolithic communities are the most extreme photosynthetic organisms known, surviving conditions that no plant and no macroscopic organism could tolerate. Now let the room be completely still. Notice the warmth of wherever you are lying, the softness of the surface beneath you, the air moving gently in and out of your lungs. You are as far as it is possible to be from the cold we are visiting tonight, and that contrast is part of what makes these places so remarkable to think about from a warm and comfortable darkness. The Antarctic Peninsula, the arm of the continent that reaches northward towards South America, is one of the fastest warming places on Earth. Over the past half-century, average temperatures on the Antarctic Peninsula have increased by approximately 3 degrees Celsius, nearly 5 times the global average rate of warming. This warming has had dramatic and visible consequences. Ice shelves that have been stable for thousands of years have collapsed in a matter of weeks. The Lassen B ice shelf, approximately 3,250 square kilometers of ice that had existed for at least 10,000 years and possibly much longer, disintegrated in 35 days in February and March of 2002. Satellite imagery of the collapse showed the ice shelf breaking into thousands of small icebergs over little more than a month, in a disintegration so rapid that glaciologists who had been monitoring the shelf condition were genuinely surprised by the speed of the event. The loss of ice shelves is significant beyond the visual drama of their collapse. Ice shelves are floating extensions of the glacier flowing from the interior, and they act as buttresses, holding back the glacier behind them like a plug in a bottle. When an ice shelf collapses, the glacier that fed it accelerates dramatically, and the ice that was previously held back on land begins moving into the ocean faster, raising sea levels. After the collapse of Lassen B, the glacier behind it accelerated their flow by up to 8 times, contributing ice to the ocean that would not have reached it had the shelf remained. The ice shelf is not simply floating ice. It is a break on the ice behind it, and its loss removes a restraint that had been in place for thousands of years. The emperor penguin is the only animal that breeds during the Antarctic winter, and the strategy it uses to do so involves a feat of physiological endurance and collective behavior that has no equivalent in the vertebrate world. Emperor penguins breed on the sea ice around Antarctica, walking up to 120 kilometers from the open water to reach their breeding colonies in the interior of the sea ice where the ice is stable enough to last through the breeding season. The male emperor penguin incubates the single egg on his feet under a brood pouch for approximately 6 to 5 days through the Antarctic winter, when temperatures can drop to minus 60 degrees Celsius and winds can reach 200 kilometers per hour. During this entire period, the male does not eat. He loses approximately 40% of his body weight, surviving entirely on the fat reserves he accumulated during the months of summer feeding. The males huddle together in groups that can number thousands of individuals, rotating slowly from the exposed outer edge of the huddle to the warmer interior in a coordinated movement that distributes the cost of exposure evenly across the entire group. The temperature at the center of a large emperor penguin huddle can be as much as 37 degrees above the temperature of the air outside it, and the energy saving from huddling rather than standing alone can be the difference between surviving the winter and starving to death before the egg hatches. When the chick hatches, the female returns from the ocean precisely timed to the hatching, walking or tobogganing on her belly across the sea ice to relieve the male, who then makes a long journey back to the water to feed for the first time in more than 2 months. The precision of timing required for this handover, in a landscape without landmarks, in conditions that disorient human instruments, and across distances of over 100 kilometers, is achieved by sound. Each emperor penguin has a unique call that its mate can identify among thousands of identical-sounding calls in a colony of tens of thousands of birds. The Southern Ocean that surrounds Antarctica is the most biologically productive ocean on Earth, and its productivity is driven by a combination of oceanographic processes that make it unique among the world's ocean basins. The Antarctic Circumpolar Current, the same current that thermally isolates Antarctica, is the largest ocean current on Earth, carrying approximately 130 times the combined flow of all the world's rivers. As this current flows eastward around the continent, it drives a process called upwelling, in which deep, cold, nutrient-rich water from the deep ocean is brought to the surface. These nutrients, particularly iron, nitrate, and phosphate, fuel the growth of phytoplankton in the surface waters during the Antarctic summer, when 24 hours of daylight provides abundant energy for photosynthesis. The phytoplankton blooms that develop in the Southern Ocean are visible from satellites as vast green patches spreading across hundreds of thousands of square kilometers of ocean. These blooms form the base of a food web of extraordinary richness, supporting Antarctic krill, the small crustaceans that are among the most abundant animals on Earth by biomass, which in turn support everything else in the Southern Ocean food web, from fish and squid to penguins, seals, and the great whales. The blue whale, the largest animal that has ever lived on Earth, feeds almost exclusively on krill, consuming up to 4 tons per day during the summer feeding season in the Southern Ocean. The productivity of the Southern Ocean is not simply a biological fact of interest to marine biologists. It plays a critical role in the global carbon cycle, because the phytoplankton that grow in it absorb carbon dioxide from the atmosphere through photosynthesis, and when they die they sink, carrying that carbon with them to the deep ocean floor in a process called a biological pump that removes carbon from the atmosphere on timescales of thousands of years. Antarctica has no indigenous human population and no permanent human residence, but it has a political and legal status unlike any other place on Earth, governed by a treaty system that has been described as the most successful example of international environmental governance ever achieved. The Antarctic Treaty, signed in 1959 by 12 nations that were active in Antarctic research during the International Geophysical Year of 1957 and 58, came into force in 1961 and has since been joined by 42 additional parties. The treaty designates Antarctica as a zone of peace, prohibiting all military activity, nuclear testing, and the disposal of nuclear waste. It establishes freedom of scientific research and the exchange of scientific data between nations. It sets aside all territorial claims for the duration of the treaty, allowing nations that claim Antarctic territory and nations that dispute those claims to coexist and collaborate without resolving their underlying disagreements. The treaty has been strengthened over the decades by additional protocols, most significantly the Protocol on Environmental Protection signed in 1991, which designates Antarctica as a natural reserve devoted to peace and science and prohibits all mineral resource extraction activity for a minimum of 50 years. Antarctica is the only place on Earth that is not owned by any nation, not administered by any national government, and not exploited for its resources, governed instead by a collective agreement of the international community. Whether this arrangement will survive the pressures of climate change, the discovery of significant mineral or energy resources beneath the ice, and the changing geopolitical landscape of the 21st century is one of the most important questions in international environmental law. The exploration of Antarctica in the early 20th century produced some of the most dramatic, heroic, and tragic expeditions in the history of human endeavor, and the story of a race to the South Pole is one that loses none of its power in the retelling. The Norwegian explorer Roald Amundsen and the British naval officer Robert Falcon Scott both set out for the South Pole in the Antarctic summer of 1911-12, each leading an expedition that represented the culmination of years of preparation and national ambition. Amundsen's approach was methodical and deeply practical. He used dog sledges, dress and clothing modeled on that of the indigenous peoples of the Arctic who had evolved it for exactly these conditions, and he planned his route and his food depots with a precision that left very little to chance. His team of 5 men reached the South Pole on the 14th of December 1911, planted the Norwegian flag, and returned to their base camp without losing a single man. Scott's expedition was characterized by different choices, relying partly on motor sledges that failed in the cold and on ponies that were unsuited to Antarctic conditions, and making decisions about route and food depots that in retrospect left the team with insufficient margin for error. Scott and his 4 companions reached the South Pole on the 17th of January 1912, 34 days after Amundsen, to find the Norwegian flag already there. On the return journey, weakened by insufficient food, frostbite, and appalling weather, all 5 men died. Scott's last diary entries, written when he was too weak to move and certain he would not survive, remain among the most affecting documents in the literature of exploration, a record of extraordinary courage and extraordinary regret, written in a tent on the Ross Ice Shelf in conditions that no reader of them has ever experienced. Drift a little deeper now. The cold we are describing is so far from where you are that it is almost impossible to hold in the mind, and that distance is part of what makes this moment so comfortable. You are warm, and the continent we are visiting is the coldest place on Earth, and you can visit it tonight from exactly where you are. The ice cores drilled from the Antarctic ice sheet are among the most important scientific archives on Earth, and the climate record they contain stretches back 800,000 years, covering 8 complete cycles of glaciation and warming that preceded the climate in which all human civilization developed. As snow falls on Antarctica and is compressed into ice over thousands of years, it traps tiny bubbles of air that contain samples of the atmosphere at the time the snow fell. By drilling down through the ice and analyzing these air bubbles, scientists can measure the concentration of greenhouse gases in the atmosphere at intervals throughout the past 800,000 years with precision that no other archive can match. The ice cores from Dome Sea in East Antarctica, drilled as part of a joint European project in the early 2000s, provide the longest continuous climate record from any ice core, and they have produced findings of fundamental importance. The concentration of carbon dioxide in those ancient air bubbles never exceeded approximately 300 parts per million during the entire 800,000-year record, cycling between approximately 180 parts per million during the coldest glacial periods and approximately 280 parts per million during the warmest interglacials. The current concentration of carbon dioxide in the atmosphere is above 420 parts per million and rising, a value that has not been reached in the geological record for at least 3 million years and possibly much longer. The ice is not simply a climate record. It is a benchmark, a precise measurement of what the atmosphere contained before the Industrial Revolution altered it, and the departure from that benchmark that the ice cores document is one of the most important numbers in contemporary science. The Ross Ice Shelf is the largest ice shelf in Antarctica, approximately the size of France, and it sits at the edge of the Ross Sea, floating on the ocean while remaining attached to the glacier of the West Antarctic ice sheet that feed it. The underside of the Ross Ice Shelf, which extends to depths of several hundred meters below sea level, is one of the least explored environments on Earth, and what has been found there has repeatedly surprised the scientists who have managed to access it. In 2015, a team of researchers drilled through 840 meters of ice on the Ross Ice Shelf and lowered a camera into the water beneath. They expected to find a cold, dark, nearly lifeless environment. Instead, they found a fish, a ghostly white nototheniode, swimming in water at -2 degrees Celsius in total darkness 800 meters below the ice surface and hundreds of kilometers from the nearest open water. The discovery was unexpected not simply because life was present, but because the fish was found in conditions where no food source was apparent, and where the distance from any productive surface water was so great that the fish's presence there could not easily be explained by the oceanographic models available at the time. The discovery prompted a reassessment of how widely life can distribute itself in the Southern Ocean beneath the ice, and it remains one of the most striking individual observations in Antarctic biology. The geology of Antarctica beneath the ice is far more varied and complex than the featureless white surface above it suggests, and the picture that has emerged from radar mapping, ice core analysis, and geological surveys of the exposed rock at the continent's edges is of a continent with a rich and complex geological history. East Antarctica is one of the oldest geological terrains on Earth, composed of ancient Precambrian rocks similar in age and character to the old stable cores of other continents, with some regions estimated to be over 3 billion years old. West Antarctica is geologically much younger and much more complex, composed of several distinct tectonic blocks that were assembled by plate tectonic processes over the past few 100 million years. Beneath the West Antarctic ice sheet, radar surveys have revealed a landscape of mountains, valleys, and plains of considerable topographic relief, including the Gambotse mountain range in East Antarctica, a mountain chain comparable in scale to the Alps that has been completely buried under ice for approximately 34 million years and whose peaks have not been touched by sunlight since Antarctica's glaciation began. The discovery of the Gambotse Mountains, first detected by Soviet researchers using seismic measurements in the 1950s and confirmed by modern airborne radar surveys in the 2000s, was described by the researchers involved as a discovery of a ghost mountain range, visible only through the ice that has entombed it for longer than any other hidden landscape on Earth. The mountains are real, their glacially sculpted peaks and valleys precisely mapped by radar, but they are as inaccessible as the surface of another planet. Antarctic krill are among the most important organisms on Earth, and their role in the global carbon cycle, in the Southern Ocean food web, and in the regulation of the ocean's chemistry gives them a significance out of all proportion to their size. Antarctic krill, Euphorsia superba, are shrimp-like crustaceans approximately 6 centimeters long and weighing roughly 2 grams each, yet their total biomass in the Southern Ocean is estimated at somewhere between 300 and 500 million tons, making them one of the most abundant animals on Earth by total weight. Every animal in the Southern Ocean food web depends on them, directly or indirectly. Penguins, seals, fish, squid, and the great whales all eat krill or eat animals that eat krill, and the removal of krill from the Southern Ocean would cause the entire food web to collapse. But krill perform an additional function that has only recently been appreciated. They feed on phytoplankton in the surface ocean during the day and then dive to deeper water at night to avoid predators, releasing their feces in the deep water rather than at the surface. These fecal pellets are dense enough to sink quickly, carrying the carbon that the phytoplankton had absorbed from the atmosphere down into the deep ocean before it can be released back to the surface. This process, called a biological pump, is one of the primary mechanisms by which the ocean removes carbon from the atmosphere on long timescales, and krill are a major contributor to it. A decline in krill populations would therefore not only affect the animals that feed on them, but would reduce the efficiency of the Southern Ocean's carbon pump, allowing more carbon to remain in the atmosphere and potentially accelerating the warming that is itself one of the primary threats to krill populations. The krill is not simply food for penguins. It is a small crustacean whose behavior is helping regulate the chemistry of the atmosphere of an entire planet. The wind of Antarctica is not simply cold. It is a geological force, a physical feature of the landscape with a name and a character of its own. Katabatic winds, from the Greek word for going downhill, form when the air above the high interior plateau of Antarctica cools and becomes denser than the air below it, and flows downhill under gravity toward the coast. These winds can accelerate to extraordinary speeds as they funnel through valleys and over the edges of the ice sheet, reaching velocities of over 300 kilometers per hour in the most extreme recorded events. The Commonwealth Bay area of East Antarctica, where the French explorer Jules Dumont d'Urville named the area Adélie Land after his wife, and where Douglas Mawson's Australasian Antarctic expedition of 1911 to 14 established its base, experiences average wind speeds that make it the windiest place on Earth at ground level, with average annual wind speeds of around 80 kilometers per hour and gusts regularly exceeding 200 kilometers per hour. Mawson described the experience of living in these winds in his account of the expedition with a vividness that makes the survival feel miraculous. Men were blown off their feet. Ropes had to be strung between buildings so that the scientists could pull themselves from one to another without being carried away by the wind. The noise was constant and overwhelming, a physical presence as much as a sound. And the cold that it carried was not the passive cold of a still, frozen day, but an active, aggressive cold that found every gap in clothing and every moment of stillness. The katabatic wind of Antarctica is not weather in the sense that weather is experienced anywhere else on Earth. It is one of the defining physical forces of the continent, as fundamental to Antarctica as the ice and the darkness and the silence that exists only in the brief moments when the wind pauses. Let the warmth of wherever you are hold you completely now. There is nothing to do, nothing to manage, nothing to prepare for. The continent we are visiting is impossibly far away. Its cold impossibly far from the air you are breathing. Let that distance be a comfort tonight. Let the darkness here be entirely different from the darkness there. Yours is warm and still and close and safe. The aurora australis, the southern lights, are the Antarctic equivalent of the aurora borealis of the northern hemisphere, and in the deep Antarctic winter, they are among the most spectacular light displays visible from anywhere on Earth. The aurora forms when charged particles from the solar wind are guided by the Earth's magnetic field into the upper atmosphere near the poles, where they collide with atoms and molecules of oxygen and nitrogen and excite them to emit light as they return to their ground state. The specific colors produced depend on which gas is excited and at what altitude. Oxygen at around 100 kilometers altitude produces the most common bright green. Oxygen at higher altitudes produces red. Nitrogen contributes blues and purples. The patterns shift and dance in seconds as the flow of solar particles fluctuates and as the geometry of the magnetic field changes, producing displays that range from a simple green arc near the horizon to full sky curtains of moving color that fill the entire dome of the sky above the observer. The aurora australis can only be observed from high southern latitudes, and for the researchers who spend months at Antarctic stations through the winter, the auroras are one of the most powerful compensations for the cold and the darkness and the isolation that defines Antarctic winter life. Descriptions of particularly dramatic auroras in the diaries and memoirs of Antarctic expeditioners across a century of wintering return repeatedly to the same vocabulary, the inadequacy of words, the sense of being in the presence of something that exceeds what language was built to describe. The aurora does not simply illuminate the sky. It transforms it into something that people who have seen it say they cannot adequately explain to anyone who has not. The ozone hole above Antarctica is one of the most significant environmental discoveries of the 20th century, and the story of its discovery, the identification of its cause, and the international response to it is one of the few genuinely successful examples of humanity identifying a global environmental problem and taking effective collective action to address it. The ozone layer in the stratosphere, at altitudes of approximately 15 to 35 kilometers, absorbs a majority of the sun's ultraviolet B and C radiation, which would otherwise reach the surface in quantities sufficient to damage DNA in living cells and suppress immune systems in animals. In the early 1980s, British researchers at Halley Research Station in Antarctica noticed that the concentration of ozone above the station was dropping dramatically each spring, reaching levels far below anything that had been recorded previously. The discovery, published in 1985, was initially met with skepticism, partly because the ozone monitoring satellites of the time had been programmed to flag unusually low values as instrument errors, and had therefore been systematically discarding the data that showed the hole. When the satellite data were reanalyzed without this filter, they confirmed that a massive area of depleted ozone was forming over Antarctica each spring, a hole in the ozone layer larger than the continent of North America. The cause was identified as chlorofluorocarbons, synthetic chemicals used widely in refrigerants and aerosol sprays, which release chlorine into the stratosphere where it catalyzed the destruction of ozone. The discovery prompted the Montreal Protocol of 1987, which phased out the production of ozone-depleting substances, and the ozone hole has been slowly recovering since then, projected to return to pre-industrial levels by the middle of this century. It is a rare and genuine example of a global environmental problem being identified, understood, and addressed within a human lifetime, driven by science done at a research station at the edge of the world. The sea ice that forms around Antarctica each winter and melts each summer is one of the most dynamic and least understood components of the Antarctic system, and its behavior has consequences for ocean circulation, for the biology of the Southern Ocean, and for the climate of the entire planet. Each winter, the ocean around Antarctica freezes to produce a ring of sea ice that at its maximum extent in September covers approximately 18 million square kilometers, nearly doubling the size of the white area visible from space. Each summer, most of this ice melts, retreating to a fraction of its winter extent. The formation of sea ice is not simply the freezing of seawater. As sea ice forms, it excludes the salt from the ice crystals, leaving behind very cold, very salty, dense water that sinks to the deep ocean floor and flows northward along the bottom of the ocean in a current that reaches every ocean basin on Earth, driving the global thermohaline circulation, sometimes called the ocean conveyor belt, that distributes heat, nutrients, and oxygen around the entire world ocean. Without the dense, salty water produced by Antarctic sea ice formation, the global ocean circulation would slow dramatically, affecting the climate of regions as far away as northwestern Europe, where the warmth transported by ocean currents contributes significantly to the relatively mild temperatures of countries whose latitudes would otherwise produce much colder conditions. The sea ice of Antarctica is not simply ice at the edge of a cold continent. It is a switch in the global ocean circulation, and changes in its extent and formation rate have consequences that propagate through the ocean system for decades. The story of the Antarctic meteorites is one of the most productive intersections of geology, planetary science, and fortunate geography in the history of science. Antarctica is the best place on Earth to find meteorites, for reasons that are entirely practical. Meteorites fall uniformly over the Earth's surface at a rate of approximately 34 to 43,000 meteorites, weighing more than 10 grams per year. On most of the Earth's surface, they quickly weather, become buried, or are simply lost among rocks that look similar. In Antarctica, the dark meteorites stand out against the white ice and snow, and the movement of the ice sheet concentrates them in predictable locations. As ice sheets flow from the interior toward the coast, they sometimes encounter buried mountain ranges whose peaks protrude through the ice. The ice cannot flow over these obstacles and instead flows around them, and the oldest, deepest ice is brought to the surface and ablated away by the wind, concentrating the meteorites that were embedded in it at specific sites called blue ice areas near the nunataks. Since systematic searches began in the 1960s and 70s by Japanese and American researchers, more than 4,000 to 5,000 meteorites have been recovered from Antarctica, including pieces of the Moon, pieces of Mars, and fragments of virtually every type of asteroid body that formed in the early solar system. The Martian meteorites recovered from Antarctica have been among the most scientifically valuable, providing rock samples from Mars that can be analyzed in Earth laboratories with instruments far more sophisticated than anything that has yet landed on Mars itself. Antarctica is delivering pieces of other worlds without the expense of a spacecraft to retrieve them. The coldest temperature ever recorded on Earth was measured at the Soviet Vostok research station in Antarctica on the 21st of July 1983 at -89.2 degrees Celsius. This temperature is so far below anything experienced in ordinary life that it is almost impossible to place in any meaningful context. At this temperature, exhaled breath freezes before it disperses. Exposed skin develops frostbite within seconds. The fuel for vehicles solidifies and must be kept heated to remain functional. Metal becomes brittle and can shatter with the application of force that would be entirely manageable at warmer temperatures. Standard Antarctic outdoor clothing, designed for temperatures down to around -50, is insufficient. The air at this temperature has so little energy in its molecules that sound does not carry well, and the world takes on a muffled, deadened quality. The atmosphere is so dry that the moisture in eyes and nasal passages sublimes directly into the air without passing through a liquid phase. Satellite observations have subsequently recorded even lower temperatures at the surface of the East Antarctic ice sheet, reaching approximately -98 degrees Celsius in measurements made during clear winter nights when the snow surface radiates heat into the sky and cools to temperatures that approach the lowest possible for a surface on Earth under natural conditions. At these temperatures, the air above the surface is actually warmer than the surface itself, an inversion of the normal atmospheric profile that is driven by the extraordinary rate at which the snow surface can radiate energy into the clear, dry Antarctic sky. The coldest places on Earth are not in a mountain pass or the poles defined by latitude, but on the high interior plateau of East Antarctica on a clear winter night, in a darkness so complete and a cold so profound that it represents the closest thing to the environment of deep space that exists on the surface of this planet. Everything about Antarctica is superlative. Its ice is the deepest in the world. Its winds are the strongest. Its cold is the most extreme. And the darkness of its winter is the most complete of any inhabited place on Earth. 6 months of night broken only by the shifting curtains of the aurora and the stars that never set because the atmosphere is too dry and too clear to blur them. And yet people go there and stay and return. The 100 or so researchers who winter at Antarctic stations each year come from every scientific discipline, drawn by the unique scientific environment that Antarctica provides. They endure months without sunlight, extreme isolation, confinement in small communities with the same people for months on end, and physical conditions that require constant vigilance and preparation. The psychological challenges of Antarctic winter over, the term used for the experience of remaining at a station through the dark months, have been studied extensively by researchers interested in the effects of isolation, confinement, and light deprivation on human psychology. The third quarter phenomenon, a documented pattern in which morale and cognitive performance in isolated groups declines in the third quarter of an extended confinement, was first observed in Antarctic winter over cruise and has since been studied in analogous conditions, including submarine service and long-duration spaceflight. The psychological demands of Antarctic winter over are considered directly relevant to the planning of human missions to Mars, where the crew would face similar or greater isolation, confinement, and distance from Earth for durations of 1 to 3 years. The people who winter in Antarctica are not simply enduring hardship in the name of science. They are serving as inadvertent subjects in one of the most important human factors research programs for the future of human spaceflight. The night is very deep now, and you have come a very long way from the surface of the ordinary world. Let the loss of anything you were carrying today dissolve completely. The Antarctic winter is dark for 6 months, and in that darkness the researchers in their small, lit stations are doing something that humans have always done in the dark, waiting for the light, doing their work, keeping each other company, listening to the wind against the walls and the walls holding. You are doing your own version of that tonight, in your own lit warmth, waiting for the morning that will come without fail, held by walls that are doing their quiet work of keeping the outside out. Everything you need tonight is already here. And so we drift gently back from the bottom of the world, rising slowly through the layers of cold and dark and ice toward the surface, carrying with us everything we found in the deep. We descended through 3.7 kilometers of ice to reach a lake that has been sealed from the sky for 20 million years and may hold organisms that have never encountered light. We walked across the dry valleys, the most Mars-like landscape on Earth, and found life living inside the rocks themselves. We watched the emperor penguins huddle through the darkest winter in any vertebrate's life, each one rotating from the cold edge to the warm center in a collective patience that produced something warmer than any single bird could generate alone. We read 800,000 years of atmospheric history from the air bubbles trapped in ice and found that the atmosphere has already moved outside the range of everything in that record. We discovered mountains the size of the Alps that had been buried in ice since before our species existed, and found fish swimming in water so cold and so dark and so remote that nothing in our model predicted them. We traced the krill that sustains every large animal in the Southern Ocean, and found it also quietly regulating the chemistry of the entire planet's atmosphere. We felt the katabatic wind accelerate down the slopes of the plateau and understood that this was not weather in any ordinary sense but the continent itself exhaling. We found meteorites from Mars lying on blue ice, delivered from another world without a spacecraft to carry them. And we understood that Antarctica, which looks like an ending, a place of nothing, a continent of negation, is one of the most important, most complex, and most consequential places on the entire surface of this extraordinary planet. It is not at the end of the world. It is in many ways at the center of everything the world is doing, quietly, in the cold and the dark, as it has been for 34 million years. If you enjoyed this sleepy journey, you can support the channel by liking, subscribing, or leaving a calm little comment before you rest. It helps more curious minds find their way here. And if you are still awake, there's another video waiting on your screen, ready to carry you onward into another corner of science. But for now, let the questions loosen their grip. Let your shoulders soften. Let your jaw unclench. Allow your breathing to slow, steady, and deepen. Picture the ice shelf at the edge of Antarctica on a clear winter night, the aurora moving green and purple above it, the stars cold and absolutely sharp in an atmosphere too dry for any haze, the ice below perfectly still and the lake beneath it perfectly dark, and the organisms in that lake moving very slowly, in a world that has not changed in 20 million years. They have no knowledge of the night above them. They have no concept of the ice that covers them, or the sky above the ice, or the stars above the sky, or the warmth of a room in a distant country where someone is listening to their story. They simply continue, in their cold and their dark, doing what they have always done. And tonight, that is exactly what you can do. Simply continue, in your warmth and your quiet, doing what you have always done when the day is done and the body finally asks for rest. Sleep well, and good night.